And all of these that basically all of the things that I have from now on, this is more or less part of the CIE Joint Technical Committee on Sparkle and Graininess, where we are really trying to come up with a document that's going to be open and that from where everybody can read and measure and do the same thing, so that we have comparable measurements, comparable measurement scales, and also traceable to the standards. So let's start with Spakle. So for Spakle, we learned that we need a light source, which is directional. So we have just one light source, one light source. The light goes onto the sample, and what we need to measure is HDR camera. So because this is a texture, it's not, you cannot just average over the whole area. We really need that spatial resolution as well. And the only way to get this is to measure with the camera. And it has to be HDR, so high dynamic range camera, simply because when you have a dark surround and then you have this bright spot, you will never be able to really measure, to capture the whole range of this sparkle if you don't have high dynamic range. But then on the same side, just heads up, HDR is every person is almost having their own HDR algorithm. But okay, so we have the light source, we have the sample, we have the camera, and what we do is we measure the sample. So we have the sample, we subtract the dark signal, and then we divide everything with the reflectance standard that is also subtracted with the dark signal. And then in the end, we multiply this with the luminance value of our reflectance standard that has to be known a priori. Okay? And here I just made this visual just for you to see that the images, so the sample, the white standard, and then the dark signal, they are images that we're taking. And then the luminance value of reflectance standard is taking the same for the whole area that we're looking at. Okay, and in the end, what we get is this luminance factor image. So we get the whole spatial resolution of the luminance factor image. Okay. The sample and the reflectance standard have to be measured at the same in the same conditions. Okay, so you just remove the sample and you measure the reflectance standard. That's important. And another important thing is that we're talking here about luminance. So that means spectrally integrated quantity. Okay, and this is what we have here. So this is really, it depends. So this is the reflectance of the sample. We multiply it with the spectral distribution of the light source, and we also multiply it with the V lambda. Okay, and then we integrate it over the visible range, and we get the luminance factor image. So how we do this is we need to have an HDR camera that has a V lambda filter, so that the response of the camera is V lambda, and we need to have a light source that is the same as the normal light source with the standard conditions. And if we don't have this, then we can still calculate a correction factor that just goes, we just multiply it, and we take this spectral mismatch correction factor. Okay, so it's not a big deal if we don't have exactly the V lambda camera, but we need to be really aware of it, and we need to then correct for this spectral mismatch. So in the end, we have made a picture, we have the luminance factor image. Now we can say, now what? Okay, so we have this image. It's a false color luminance factor image, and we can see a few of these bright spots over here. So what we do now with this is we take the pixel with the maximum value. So let's say this is the pixel with the maximum value. We define an elementary area that is small enough and big enough to really capture one sparkle. And we average the luminance factor of that. We average the pixels inside this elementary area, and now this is our luminance factor of the elementary area. Once we do that, we set this area to 0, and then we repeat the process. So we find the next pixel with the maximum value. We take the average value, and we put that to 0, and so forth and so forth. So we just keep on doing it until basically the whole of this image is black. So in the end, what we have is we have these luminance factors for a lot of elementary areas. Okay, and now what we do with this is, so the whole principle, what we want to see is, can we see this sparkle or not? Okay, can we see this tiny bright spot, or is it just the same as the background? So in order to do that, we need to compute the contrast. And we do this as basically for each elementary area, we compute the illuminance contrast. So we take this luminance factor of an elementary area, we subtract the background luminance factor, and then we also divide it with the background luminance factor. And then in the background luminance factor is nothing else than the luminance factor that is coming from the background and not from these tiny bright spots. And then if we're interested in the visibility basically of the luminous point, we need to we use this formula, which just tells us that if our contrast is bigger than a threshold contrast or not. This threshold contrast, it has a lot of math behind it, so I won't go into that. But basically, really what we're trying to see is if this visibility is higher than 0, then we see the sparkle. If it's lower than 0, it's not a sparkle. We don't see it as this bright spot. Now I'm just repeating the two formulas here. And I'm just, so we have this, when we have this visibility, it's basically, again, we have a lot of values, and what we can do is we can compute the quartiles of this visibility, and the measurements, the measurement in the end for sparkle, what we have is this second quartile of sparkle visibility, or you can also work with all of them. And the other thing that is the measurement is the sparkle density, which just, it counts the number of the visible luminous points per square millimeter. So you always need to have, you need to know how big your sample is. You just count the number of these points that have the visibility over 0, and then you just compute that number divided by square millimeter, and you have the sparkle density. So this is all described in the paper, in this, on the one that I was mentioning before at the start. And this is open, and what this means is that measurements of the same thing can be done across different NMIs, different designated institutes. And then we can compare our devices. And this is exactly what we did here. So this is an image, a figure from this paper from Metrologia, where we had 4 different institutes that were part of this measurement, basically comparison, with different samples. And we can see here we have plots for 3 different geometries. We're plotting this Spakle density, and then this second quartile of the basically Spakle quantity is what we're calling it, for 3 different illumination angles. That's what we did. And this is basically the whole point. We need to have measurements that are defined, open access, and then we can do measurements across different institutes and see if we can match it or not. So we have the Spakle. Now we can do the same for graininess. With the graininess, so these equations are basically the same as for the Spakle. What is different is the measurement geometry. So for the Spakle, we really needed this direct illumination, but for graininess, we need diffuse illumination. And that means using an integrating sphere. So we have here the integrating sphere, we have the sample just as before, and we have the light source that's coming in. And you can see here that the camera is still an HDR, but you can see that it's not at 0 degree. So it's not looking directly perpendicular to the sample, but it's shifted to the 8th degree. And that's basically just done so that we avoid any specular reflections. So for example, if you have very, very glossy samples, and you look with the camera perpendicular to the sample, then you can see the reflections from the lens, from the objective, and everything else if you're looking directly to the sample. So it's better to avoid this altogether, to put the camera at 8 degrees, then you don't have it, and it's one of the standard measurement geometries for diffuse diffuse measurements anyway. So you have the camera, 8 degrees, sample, light source. You repeat the process. So again, you measure the sample, you measure the reflectance standard, and here with the dark signal, you just remove the sample, you take it all the way out. The light source is still on, and then you measure the dark signal just to avoid any stray light that might also come to the camera. And again, make sure the camera should have a V lambda filter. The light source should be fine. So otherwise, you just do a spectral mismatch correction factor. Okay. So yes, now we've measured it. We have the graininess, and we have the pictures. So here we have a set of measurements, a set of graininess images that from a set of samples, where we have basically from low graininess up to high graininess. Okay. And what we can see is really this salt and pepper appearance that we're seeing. And it's so we have to deal with this in a different way than what we did with the Spakle, because this is more or less just spatially correlated lightness variations. Okay, and so what we do is we take one image and we compute the power spectral density of that image. And here we have the graph where we're showing the logarithmic of this power spectral density. As a on the x-axis, we have the spatial frequency, and we have this for all 9 of the samples that were shown before. And also we have this one is just from the white sample where we have no graininess whatsoever. And now what we're interested in, it's not just the whole range, it's just we need to find a range where we can really see this difference, where we have the spatial frequencies that are correlated with the graininess itself. So we pick one spatial frequency and the other spatial frequency, and we basically integrate this power spectral density. And this is then called the graininess variance. Okay, so we just select 2 spatial frequencies. This is done with the relation with the visual experiments, and you integrate. And then once you have this variance, what we have as a measurement is this graininess quantity, where we have the variance, and then we have these 2 betas as well. We have from the background, and we have, this is the average luminance factor. And we, no, sorry, this is the average one, and this is a fitting parameter. Sorry about that. So, and we compute this, and then this in the end is our graininess quantity. Okay. So that's a lot of math. But the good thing is this math is published. Everyone can read about it, and everyone can do the measurements now and do their own calculations of the sparkle and the graininess. But if we just have the measurements, that's not enough. We need to also compare it with the visual experiment. And this is a whole different topic. Here I'm just briefly mentioning this. So we have visual experiments for sparkle, we have visual experiments for graininess. They're different. They take quite a lot of effort because it needs a lot of experiments itself. They're quite demanding. So, but it's fun. And in the end, what you need is you want to see how the perception depends on the size of the pigment, the shape, the concentration, the overall sample lightness, as well as the light source and also the illumination level. So there's quite a lot of factors that really influence this perception in the end. You can, if you're interested about that, here are the 2 papers that are really presenting these 2 topics. But the main thing here is what they found is that perception depends mostly on the size of the effect pigment. So the bigger the size, the more we perceive the sample as having higher sparkle or higher graininess. And this also correlates, if you remember at the beginning of my talk, I was talking about the size of the effect pigment. If we have a bigger size of the effect pigment, there's more light specularly reflected directly from the pigment and less light is scattered off the edges. So long story short, we have a better, we have the perception of higher sparkle and higher graininess. Now, so we have on one side, we have this visual experiment. On the other side, we have the measurements and the measurement scans. And now we just have to put the 2 together. And this was done in this paper here in the Optics Express. So where we have really, we have these 2 different figures. We have on the left for the sparkle. So where we have really the sparkle quantity. So this is really from the measurements, this second quartile of sparkle visibility. And on the y-axis, we have the visual sparkle, so coming really from the visual experiment. And we can see that for this set of samples that were both measured and the visual experiments were done on the same set, we can see it has a very nice linear correlation, between the measurements and the visual experiments. And the same thing happens for the graininess, where again, we have this graininess quantity coming from the measurement side, and then we have the visual graininess coming from the visual experiments, and we see this nice linear correlation. So this is all what has already been done. Now, if we just take a look at what is still there to do, all of this time I wasn't really mentioning the color in any of my talk. So this has to come into the future. We need to work on this. And the other thing that we have to consider is what we're calling the living sparkle. So here we really see when we change the light source, the illumination, this sparkle travel around. So this is called this living sparkle, and we need to in the future work on this as well. So there's still a lot of things to work on this, but we're making progress, and we're on our way. Let's do it like this. So thank you very much for your attention, and that's all from my side.
Thank you. Thank you very much, Nina, for this very nice talk. And I will see if there is any question in the audience. Yes.
Thank you, Nina, for your talk. I have a question concerning smaller size interferential pigments. Do you know of people that work on, or do you plan to work on the appearance of smaller size interferential pigment where you don't see the sparkle anymore, but can maybe have films that start looking more metallic like? So I don't know if you have any comments on this.
So my question back would be how small size we're talking about. And let me just answer that you need to have a certain size to really see the sparkle. Okay, if it's very small and if it's really just everywhere, at one point you just see it as uniform. You don't really see these sparkles anymore. So you really need to be in some range to
yes,
have
that's exactly the sizes that I'm mentioning. So it's when you don't see the pigment anymore, you don't see like a strong sparkle or with like a glittering effect, but you can have interferential pigments that are, I don't know, like hundreds of nanometers size. So they're still interferential, and they have more of a uniform, color. There's no, you don't see the pigments anymore. However, they have an impact on the appearance of the deposit. So I don't know if you know of people that work on this kind of systems, or if it's something that could be worked on in the future.
I mean, this probably falls in this goniochromatic effects, from what I'm hearing, which is not, I mean, for sparkle to be sparkle, you really need to have this appearance of sparkle. And if you don't have this, then it's basically just a side effect that it's, it's more or less uniform. So you don't really have it. I'm not really sure. Maybe Alejandro knows if someone is.
Yes, I was here with the microphone. Yeah, answering your question, when you are using tiny flakes for interference, what you are getting is monochromatic colors, the iridescent colors like the ones that Gael has shown in the car. You know, the car he he has shown before, and all the analysis in the CIEV map on the travel of the color change, and that is related with that. The work has been done on those kind of materials with effect pigments. They don't have a sparkle, maybe, but they have iridescence. That is a very important also phenomenon that has to be measured.
So thank you again, Nina.